Hello everyone, my name is Ke Yuli from the Chinese University of Hong Kong. Welcome to my presentation on autonomous navigation of an ultrasound probe towards standard scan planes with deep reinforcement learning. Due to the advantages of portability, non-invasiveness, low cost, and real-time capabilities, ultrasound imaging has been widely accepted in many medical applications. However, the current ultrasound acquisition procedure requires trained personnel to manually navigate the probe. This will make the imaging quality highly dependent on the operator, and the heavy workload is exposing the clinicians to health risks, such as regional pain. Moreover, the frontline medical staff will be vulnerable to infectious diseases due to the direct patient contact, especially during a pandemic such as COVID-19. This motivates us to develop an autonomous method to control the ultrasound probe in routine ultrasound examinations. During the past 20 years, a large number of semi-autonomous robotic systems have been developed to allow teleoperated ultrasound imaging. However, manual operation of the probe is still required in these systems, and the remote control usually has high requirements for bandwidth and communication quality. Also, the off-site operator may have to deal with information overload during the remote control. To date, some fully autonomous robotic systems have also been proposed in the literature for different ultrasound imaging applications. While these systems can effectively follow a pre-interventional plan or cover a region of interest, they haven't investigated the interpretation of ultrasound images and the precise positioning of the probe to visualize the standard scan planes like an expert sonographer. The standard scan planes in ultrasound examinations are the important imaging planes defined by expert consensus to visualize the anatomical structures of the target tissue. These planes usually contain valuable information for diagnosis, biometric measurements, and ultrasound-guided interventions. For example, this figure shows the paramedian sagittal laminar view, which is one of the standard scan planes of the spine. In order to search for the standard scan planes in the ultrasound acquisitions, an expert sonographer will continuously observe the ultrasound images and make decisions to navigate the probe until reaching the desired position. In recent years, reinforcement learning has achieved human-level performance in solving sequential decision-making problems, where the agent learns by interacting with the environment through observations, actions, and rewards. It has been successfully applied in many real-life applications, such as mobile robot navigation and dexterous manipulation. The main idea of our proposed solution is to formulate a task of navigating the probe towards standard scan planes as a sequential decision-making problem in the reinforcement learning framework. The contributions of this work include: first, we present a deep reinforcement learning framework to control the 60 poles of an ultrasound probe based on real-time ultrasound images. Second, we propose a confidence-based method to encode the optimization of image quality in the learning process in order to improve the navigation performance. Third, a simulation environment is built with real-world ultrasound data to evaluate the method. We use SonoRL to refer to our deep reinforcement learning solution to ultrasound probe navigation. Given the ultrasound image as the observation, the agent selects the navigation action of the probe based on a deep neural network. And after the probe is moved, the agent will receive a reward which is associated with improvement of the position, orientation, and image quality. Then the agent will refine its navigation policy by updating the neural network parameters. First, we define the state of the agent as the 60 poles of the probe with the acquired ultrasound image. Moreover, we consider the problem as partially observed, which means the agent can only observe the ultrasound images to decide the movement of the probe. The actions are defined as translation, in the horizontal plane along the x and y axis of the probe, and the rotation around the 3 axes of the probe. For the state transition model, we consider 2 requirements in the real-life ultrasound acquisitions. First, after the 5D movement of the probe is determined by the selected action, we adjust the position of the probe along the z-axis to make the probe follow the patient's surface. Second, we limit the tilt angle of the probe to 30 degrees to ensure the comfort and safety of the patient. The termination conditions include A. The goal is reached. B. The number of steps exceeds limit. C. The pose of the probe converges. And D. The probe moves out of the workspace. Only the last 3 conditions will be used in the testing phase, as the goal position is assumed unknown to the agent. We design the reward function to be proportional to the amount of pose improvement of the probe, represented by the change of distance to goal in position and orientation. Here, D is the Euclidean distance between the current probe position and goal position, and theta is the minimum angle required to rotate from the current probe orientation to the goal orientation. Besides, we assign a high reward for task accomplishment and add some penalties based on the restrictions of the environment. Furthermore, inspired by the fact that the sonographer usually operates a probe to obtain clear images of the tissues while searching for the target anatomy, and avoid positions that may cause poor image quality, we propose to use the ultrasound confidence map to estimate the pixel-wise image quality based on the simulation of the physical properties of sound propagation in soft tissues, and we modify the reward function to take into account the image quality improvement ΔC. Finally, we modified the SonoNet 16 to approximate the optimal value function, action value function Q, and train the network with the deep Q-learning algorithm. The algorithm and training details can be found in the paper. We built a simulation environment with real-world ultrasound data collected from 17 volunteers with a robotic ultrasound system. The image data covering the lumbar spine were reconstructed as 3D volumes to serve as virtual patients in the simulation, and the SonoRL agents are trained to navigate towards the perimedian sagittal laminar view of the spine. The quantitative experiment results show that our method is able to perform accurate and reproducible acquisition on familiar patients, and the introduction of image quality optimization can effectively improve the navigation performance of the agent. We further compare the method with and without confidence improvement on a test case. As shown in the video, without confidence optimization, the agent only learns to care about minimizing the distance to goal, and it is finally stuck at a position with poor image quality. In contrast, the second agent is trained to be aware of both the distance to goal and the image quality when making decisions, and it will avoid the positions with bad image quality during navigation. Finally, it can successfully reach the standard scan plane. In conclusion, with this work, a deep reinforcement learning solution is proposed for autonomous navigation of an ultrasound probe towards the standard scan planes based on real-time ultrasound images. The optimization of image quality is introduced in the learning process through a confidence-based method to improve the navigation performance. Experiments in simulation using real-world ultrasound data demonstrate the effectiveness of our method. The video of this paper can be found at YouTube or Bilibili. Thanks for listening, and I hope to hear from you soon.